Ourselves where we were. Oh yes, we have 2 versions of my face on the screen this lecture. That's great. I like that. More face in the lecture. So remember what we were doing. We had this physical system, mechanical system, and we wanted to solve for what the output is, which we said was the velocity of the mass as a function of time, given a step input. So we did all of our typical modeling, got our state model, and we then found our system transfer operator as a bridge to our differential equation, input-output differential equation, which we got to be this, right? So we made a lot of progress. Now we just need to solve it, and we started that solution. So we said we're using superposition. We're going to come back to that, but suffice it to say that we chose to find the output for a step input, a unit step input. And then I told you we're going to be able to use superposition to find the full output, right? So we're going to find the output for a step input. And so we found the homogeneous solution to be this, right? And we said, okay, good, it's stable because the poles are in the left half complex plane, meaning that they have negative real parts. And it's also going to oscillate because we have imaginary parts too. So that's where we left off. So now we need to find the particular solution. Okay? The particular solution in this case is super easy. Okay? So you may recall that we have a step input, which is from 0 for time less than 0 and then 1 for time after 0. And when you use this particular solution method of undetermined coefficients that we like to use, when we have a constant value for time greater than 0, and 0 less than that, that is equivalent to assuming that your solution is going to be a constant. Okay, if you look up in our table, it has constant input, constant output. That also applies to the unit step input. You assume it's going to be constant. Of course, there is also an assumption it's going to be starting out at 0 before time equals 0 and then constant thereafter. That's the assumption that we don't always state, but that's important to keep in mind. So the particular solution, VMP, is going to be of the form K1, a constant. Okay, so we can find out what K1 is going to be by plugging this into our initial differential equation, which is this, right? So if it's a constant, this is 0, right? So second derivative of it is 0. First time derivative is 0. So this is non-zero. So we'll plug K1 in there. And then remember, all of the stuff on the right-hand side, we said we're just going to ignore all that for now and put in a unit step input over there. So that other side of the equation is just 1. Okay? So if we were to plug it in, we would get K over M times Vm, so we'll plug in K1 there, equals unit step on the other side for all time greater than 0 is just 1. We can quickly solve for K1, which is, to everyone's amazement, M over K by some crazy trickery called basic algebra.
Yeah, that's where I draw the line.
Yes, this is very hard. General solution. Yeah, I know. It's like you're really weirding me out by being back there.
Sorry.
It's okay. It's okay. It's because you wanted to find power, right?
Yes.
It's cool. I did have to figure out why. I was like, why is he sitting there? And like I see the chord. I'm like, okay. Like I can now continue with my lecture. I'm okay. I was like. I had coffee this morning, maybe some coffee breath or something. People backing away. All right, general solution, we know, is just the sum of those two, right? So Vm. So of t, you can put the subscript t or g if you want to. Vm of t is Vm h of t plus Vm p of t. Okay. I am actually going to put, in this case, I'm going to put a little subscript s for the step here, just to delineate. This is Vm, this is the general solution for the step input, right? Yeah, exactly. So we now, of course, need to know the specific solution, which is usually a pretty straightforward process of just plugging in the initial conditions, which that is what we're doing here too, but it's just going to be algebraically more complex, pun intended. So, thank you for the little laugh. So let's plug in our initial conditions, which I said are going to be 0. Okay, they're going to be 0. So we have that Vm of 0 is equal to 0. So Vm s of 0 equals 0, which tells us that 0 equals, now let's plug in our solution, our general solution, with time equals 0 in it. So that is going to be C1 e to the 0, which is 1, plus C2 e to the 0, which is also 1, plus m over k, which is equivalent to writing 0 equals C1 plus C2 plus m over k. Now, we don't have a solution for one of the constants from this like we like, because we got two constants we got to solve for. We have another initial condition, which is that the time derivative is equal to 0. So we have to take the time derivative of our general solution here and set it equal to 0. So that's where things get complicated, right? So let's do it. Vm s dot of 0, that too, equals 0. What we're saying is that 0 equals, and then now let's take the derivative of this. So the derivative of these homogeneous terms, I'm going to call this lambda 1 and this lambda 2 for this part, so I have to keep rewriting that complex number. Okay? So that's going to be C1 lambda 1 e to the lambda 1 t plus C2 lambda 2 e to the lambda 2 t plus, what is the time derivative of this constant? 0. Very good. So yeah, so when this is, oh yeah, that also I didn't plug in, these are going to be 0, right? 0 and 0. Okay. And okay. So what I can find then is I have to solve these two simultaneously. I guess it's a little bit simpler to write 0 equals C1 plus C2. Right? Oh yeah, there's some lambdas there too, right? Times lambda 1 times lambda 2. Good work, guys. Okay. Now, if we want to solve, so this is just a set of two simultaneous equations, right? So, and they're linear. Just solve for C1 and C2. Do that whatever way you want. It's really, I mean, you could do elimination here, you could do substitution, whatever you feel. The solution is actually not very hard. C2 equals m over k times lambda 1, all of that divided by lambda 2 minus lambda 1, and C1 is equal to m over k times lambda 2 divided by lambda 1 minus lambda 2. And if you evaluate C2 for those values, then we get negative 0.01 minus J 0.0028, and C1 is negative 0.01 plus J 0.0028. Okay? It's just a complex number. Now, we just need to we have our constants. They are complex, right? Which is fine. There's no reason we can't have that. What we need to do then is plug those constants back in. So technically, we have our solution, right? It's just kind of messy. So I'm going to write it all out in its glory, and we're going to want to rewrite it. Negative 0.01 plus J 0.0028 times e to the lambda 1t plus, and then we have the negative 0.01 minus J 0.0028 times e to the lambda 2t plus k over m, right? Which I should evaluate.
No, that's m over k.
Oh, it's m over k, and that you're right, and it is also I evaluate. Let's just evaluate it because I was plugging in numbers for everything else. So that's this. So this is not the way that we like to look at this solution. This isn't very intuitive to a lot of people what this function does. So we typically like to rewrite this in terms of sine and cosine.
For which we have Euler's formula.
Euler's formula, that's right. But we don't quite have something that we're ready to apply that to yet. And so what we're going to do is we're going to expand out these terms a little bit, and then we're going to contract them in. So let's unpack them and then repack them the way that we want. So what we're going to do is we're going to take the two real parts, okay, and we're going to bring them together. So notice there's a real part, an imaginary part, a real part, an imaginary part of each of these, right? Let's bring the real parts out front. So we have negative 0.01, and then we have e to the lambda 1t from this term. And then from this term we have plus e to the lambda 2t. Right? And then the imaginary term has, they both have 0. So I guess I don't put that in the parentheses. J 0.0028 times the quantity, and this one has e to the lambda 1, e to the lambda 1t minus e to the lambda 2t, still plus our little hanger-on of 0.02. Now we've got, we're getting to a point where we're looking closer to something we can apply Euler's formulas to. But lambda 1 and lambda 2 each have a real and imaginary part associated with them, right? Fortunately, they have the same real part. Remember, it was negative 1.875 real part. So we can factor that part of it out. So this is equal to negative 0.01. And then we can factor out the real part of the exponential, negative 1.875 t, right? So that's from the real part of both of these, because this one has an e to this, and then this one has an e to that. And remember, if you have an exponent that has added values in it, you can split it up into multiplication of two exponents, right? Of two exponentials. So all those little exponential and log properties, they come in handy occasionally. And what's left in here is e to the j, and then just the imaginary part, which was 6.82 t, plus e to the minus j 6.82 t. Yes, because there was a t in multiplying the real and the imaginary part. Yes. So plus j 0.0028. Same exact process here. E to the negative 1.875 t we can factor out, and left inside is e to the positive j 6.82 t minus e to the minus j 6.82 t. Okay, now this looks more complicated than what we started with, so you might think, oh my god, what are we doing? But, oh yeah, 0.02, excellent, thank you. So this term and this term are found in the Euler's formulas, okay? That's why we started rearranging these things. We knew that Euler's formulas apply to these totally imaginary exponentials, right? E to the j something, and that they need to be extracted by themselves, and then they turn into cosines and sines, right? So if you go back to Euler's formulas, then you'll see we can make the following simplification. So let's factor out, since we have this e to the negative 1.8. Oh, that's too bad. Just go sidebar here. Use the margin. E to the negative 1.875 t factors out of both of those terms, right? So let's factor it out. And then negative 0.02, so we're going to combine some terms. There's going to be two of them. 2 times cosine of 6.82 t. Now, the 6.82 is the imaginary part. 6.82 t is the imaginary part from the exponent here. So that's where that came from. This is Euler's formula that says cosine is equal to this. But there is a factor of 2, right? So Euler's formula has a factor of 2 in it, the one that has cosine equals. So you have to go back and look it up. But it has a factor of 2 that we put out front. We multiplied the 0.01 by 2. So don't forget the factor of 2. It's an important factor of 2. You'll be off by a factor of 2 if you forget it.
Stuff plus e to the negative stuff equals 2 cosine.
Yeah.
Stuff.
Yeah, exactly. So you can look that back up in the Euler's formulas. plus, and then the other term here is this one has a j associated with it in Euler's formula, so we get the j's to drop out, but j times a j is actually -1, so I'm going to just change the sign here. Minus, and then there's another factor of 2, 0.0, and then it's 5/6, which is 2 times that, times sine. So this one is sine of 6.82 t. And then we close the parentheses, and then we add our offset that we don't want to forget. And this last step, I'm just going to put here in parentheses, we used Euler in this last step. We hadn't actually used Euler up to that point, right? We finally used it. Yeah?
Would it be easier, or could you even use Euler like once you got to the homogeneous solution and switch it, and then run through it?
So you can do that. So you can start with Euler earlier on. So back up here, our homogeneous solution we expressed in terms of complex exponentials. We didn't turn it into using Euler's formulas into trigonometric. Right, but you can try to do that. You can start using it. I don't think it's easier. I don't know if there are any pitfalls that direction. I usually do it this way, but there might be some pitfalls that direction I just haven't been aware of because I haven't tried it. But
my differential teacher always, from this step, he would always go to the
trigonometric form. Yeah, which is probably totally valid to do. There's no reason to. And this is part of, I hate because a lot of students get caught up in this part. But it's too bad because it's really, I mean, all we're doing is rewriting the solution, right? There's a complex exponential form of the solution, and then there's a trigonometric form. And they're equivalent. There's no, one's not more correct than the other. But often we like to think in terms of trigonometric functions in engineering. It's just common for us to do. In physics, a lot of times they would never turn this into trigonometric. They would just always stay in the complex exponential. They are more comfortable there. So I show you how to do it, how to go back and forth, because I think it's important and you need to kind of understand the math there. And I want you to be able to do it for the exam.
What?
It's not maybe a huge surprise. It's been in the homework, I'm doing it in class. I want you to be able to do it for the exam. But it's not a super key conceptual aspect of the problem, right? There are trigonometric representations, and then there are complex exponential representations. And they're related by Euler's formulas. And that's really all that... In that one homework problem, your first homework problem, it does require another trig identity for you to recognize to split up the sinusoids. But most of the problems that I give you are not going to require you to recognize a trig identity. Like on an exam, you should be able to do the trig identity so you should be able to do Euler's identities. You should be able to do those trig identities that go from a cosine and a sine to one cosine or one sine. I gave you those in the basic math reference table. So, all right. Whew. So we did all of the maths, right? And we only solved this, mind you, for the step input. But like our input is not a step input. Our forcing function, as we like to call the right-hand side of these input-output differential equations, is not just a step. Vs is a step, right? But the actual forcing function is all this. So, did we just solve a different problem? Are we screwed?
No, we can plug in and add and multiply something like.
Yeah. So let's think back to our lesson on solving differential equations with superposition. Superposition has a lot of really interesting aspects. One of them is that if you scale the input, just scale the output by the same factor. So if superposition applies, if it's a linear time invariant system, superposition applies, and if you scale the input, so for instance, if we ignore this term here with a derivative in it for a moment, and we just focus on this one, we found the unit step output, right? So this input is a scaled version. This right-hand term is a scaled version of the step input, right? It's not a unit step, but it's a step input. So what do we know? If this was the only term that was going in, we have the step response. What is the response to this?
The step input times scale rate.
Yeah, so whatever the solution was that we got for the step input, which was this, right? We have to scale that by k over m. And we scale it by k over m, that'll give us what the step output is. So we don't have to solve it again. We just scale it. That's nice, but we have two terms. So in general, remember that superposition tells us that if you have the addition of two terms in your forcing function, then you can find the solution to one of those terms. So just put in one of them by itself, find that solution, and put in the other one by itself, find that solution, and then just add them together, right? So that's convenient. Okay. We have two. We just can find the solution to this one separately and then add it to the solution to the other one. However, we don't have the solution necessarily, so it's Vs dot is the input. So we can use yet another property, which we call the differentiation property. People are just... Are you taking off? Can you shut the door, or at least close it mostly? Yeah. Thanks. So he probably didn't think I was gonna meet him at the door and call him out. So if we're taking the time derivative of the input, we have this other property that we learned that we can just take the time derivative of the output, right? That was another, we called it, I forget which lecture it was. Do you guys remember? Let's go to the internet and let's go to notes and then post it here and blah blah blah.
Actually, sidebar. So why doesn't the notes thing that you push first take you to this page? It takes us to the second tab, and then we have to pick another tab to get there.
Because that's like a table brings you to.
Oh yeah. So you mean this? This is a table of contents. So if you want to see what the textbook is, it takes you to textbook. See what assignments are, it takes you to assignments.
It's not like a
It's a table of contents.
Yeah.
That's why it's green box around it, and it says contents. Is that also? So yeah. Okay. So you guys remember this set of notes? So this was where we did all the superposition stuff, and this is where we did this differentiation thing. Okay. So this is where it is in your notes. Point of reference for you. Okay. So take the derivative of the input, just take the derivative of the output. And we want to know what Vm is for this forcing function, like I said. So you have the time derivative, and you're adding these terms together. So you've got scaling, multiple terms, and differentiation all in one problem. Don't even accuse me of not doing the hard problems in the examples. So from superposition, we know that Vm of t, so no longer just for the unit step, we want to know for this whole thing, what Vm of t is, we can scale by b over m, so b over m scales, the derivative of the output that we have. So Vm s of t, the solution that we have up here, right? Just right here. But what do we need to do to it?
You need to take the derivative.
You need to take the derivative, so we need to dot that. And then what's the second term going to be? So we got to add. So what is the left? What's left? So k over m times just Vm s of t, and that's it, right? I mean, that's really the answer. Now, there is a lot of work that goes into actually expanding this, right? You have to take the time derivative of this, which is not hard, but it's just because we have all these numbers floating around. This is why I love to give you guys symbols. So we don't have to worry about all these numbers everywhere. It takes a lot of time to write down. Anyways, I will leave the actual crunching of that as an exercise, but we end up with 1 plus, and it's good for you to go through the crunching of it because, you know, you might need to do it sometime. Because, believe it or not, I don't teach you this just for fun. Sometimes you might need to use this stuff that I give you. Yeah. Also, maybe in your, engineering careers, you might need to calculate something. And I know that sometimes you guys feel like maybe this stuff is not going to be relevant to your engineering careers, but
at least you have to know how to tell computers to do it.
Yes, you do. Yes, you do. And voila. So what do we have? Let's interpret what this looks like. So what is that?
It's like a sine wave.
Constant. Yeah. So there's a constant offset, and then there's a decaying sine wave to 1, right? Because this is going to go to 0 eventually. This whole thing's going to go to 0. And it's going to oscillate about 1, and it's going to damp out.
So it's stable.
So it's stable, exactly, because it comes to an equilibrium value. Yeah. Okay. Whew. So, believe it or not, that was not the last thing I'm going to teach you. I know it seemed like it was going to.